Howdy. So my name is Jian. I'm an assistant professor from the School of Performance Visualization and Fine Arts. And I'm also the founding director for the Digital Twin Lab at the Texas A&M Institute of Data Science. And today, we are delighted to have Dr. Michael Grieves with us. So Michael is the pioneer in the field of digital twins and also the product life cycle management. He worked with the global technology and manufacturing companies and consulted for top organizations such as NASA and Boeing. His academic contributions are significant, with appointments at renowned institutes, including the University of Michigan and the University of Central Florida. Today, Dr. Grieves will delve into the transformative potential of digital twins, a concept he originated, and their role in driving efficient decision-making processes across various industries. Please join me in welcoming Dr. Michael Grieves. The microphone is yours, Michael.
Thank you very much. And so I will start sharing my screen. And you can tell me whether we have it up or not. So are we good?
Yes. Okay.
Great. So good afternoon, and I'm going to spend a few minutes today to talk about the digital twin driving 21st century transformation, because I think that that's exactly what this does in terms of that, and I hope to give you a feel for not only what we're doing, but why we're doing it. So as you all probably know, that the digital twin has sort of exploded in both scope and scale, and so I'll talk a little bit about the formation of it. In 2015, 2016, there weren't a lot of indications that there was adoption of digital twin. In fact, there's a podcast I do with an executive for General Motors in 2018, and I say then there was about 1 million hits if you looked up digital twin. I mean, today, if you do a Google search, is about 17 million. So the scope and scale has gone up dramatically in terms of the last few years, about the ability of being able to think about and implement digital twins. And so it started off in aerospace and automotive, but it rapidly moved into other areas. So here you'll see locomotives, power generation, ships, the ports of freight ports, oil rigs, even a digital twin of buildings and smart cities. COVID was the pharmaceuticals were developed using some digital twins of COVID. And then we have digital twin of the Earth. In fact, I gave a talk, was part of a panel for NOAA and NASA in terms of the Earth system's digital twin. I might add we have a long way to go to understand that complex system, but the work is being done in that particular area. And I had already thought at the beginning that this had kind of wide application, but I had sort of stuck to the tangible areas of digital twin because people could get their heads around having products. But we also have the ability to do intangible things. So things like logistics, the process industry per se, entire economic systems, manufacturing processes, and then what I call supply net, which is the digital counterpart to supply chains. And so if we can kind of visualize it, we can create digital twins of that kind of capability. The conceptual, the idea of digital twins was introduced back in 2002 at an SME, Society of Manufacturing Engineering Management Forum, and it didn't even really have a name at that point in time. I had PLM, Product Lifecycle Management, was a brand new discipline at that particular point in time, and this was an idea of being able to think about our ability of sort of stripping information from physical things and having them be active in virtual space or really digital space. The digital twin model of today looks like this, and it has three sort of major components. It has physical products and physical space that we've had since time immemorial and will always continue to have. And then over in the virtual space side, we have these digital capabilities of not only having the digital products, but also the digital environment. what we want to do is have a connection between these two, a permanent connection, where basically we populate the digital virtual space with data from the physical world. And then what we want to do is to use information that we generate in this digital virtual space. And we want to basically be able to use that over in physical space. And why do we want to do that? Well, we want to do that because in the 20th century and before, the only space we had to work in primarily was physical space. So when we had any kind of an idea we wanted to share with others, it had to take physical form, either a drawing or a written document or blueprints or even a physical prototype. What we want to do is we want to move work activity from the physical world into the virtual world in the 21st century. So this is a quantum leap in terms of our capability. And why do we want to do this? Well, we want to do this because we want to substitute information for wasted physical resources. And this is kind of the core premise behind not only the digital twin, but digital transformation in general. And I think this is sort of an idea that we kind of should focus on, because this is really the primary thing that's driving, as atoms increase in price and bits decrease, we have a unique capability to do something that we have only kind of done very inefficiently before. And the whole idea is about information. And if you sort of look at the literature on information, the thing was captured in a pretty good book on it, was there is a huge amount of confusion, but very little understanding and conclusions about information, what it is. And so there's all kinds of different definitions, and they vary well across the board as to what information is. And so rather than kind of fight that battle, what I kind of approach to that and say, what does information do? And from my perspective, what information does is that it basically is a replacement for time, energy, and material that we use in doing a task. And so human existence is pretty much about goal-seeking activities, tasks, while we minimize resources. So I can take any of these tasks, whether we're talking about designing a product or testing it or trying to manufacture it or even having repair it, we can divide it into two pieces, okay? The green bar that you're seeing there is using the least amount of physical resources to do that task. Everything above that is information inefficiencies. And as I say, this kind of drives our entire life in business, but on a personal basis, if we're trying to get 3 kids that are after school activities, we wind up into this problem of wasting amounts of time because we don't know things like where the practice has been shifted to or the fact the practice has been canceled. But I can take any of these tasks and I can cost that because we live in a capitalistic society. And by the way, even if we didn't, there's always a cost function we can apply to how we spend our time. Information is a replacement, not for the physical resources that we need to accomplish the task, but for the information inefficiencies. Now I'm showing the fact that it replaces all information inefficiencies, and that's never going to occur in human existence because we're never omniscient or omnipotent, which this is what this requires. The other thing is we don't have a unit of measure for information like we have for these other things, but we can get there with a proxy for hardware, software, people's time in terms of developing information. And when does this work? Well, this works when the cost of information over all the times we do these tasks is going to be less than the cost of wasting resources. So one-time task, trial and error is perfectly fine. We're not going to develop an information system for it. But if it's a repeatable task, and especially, for example, in manufacturing, we actually have a name for it. It's called lean manufacturing. But the whole idea is the cost of information, because information is not free, is going to be less than the cost of wasting time, energy, and material. And then so why has this sort of exploded onto the scene, and why now? And it goes back to having Moore's law. And Moore's law, for those of you that may not be aware of it, although it's pretty well understood, is that it's not a law, but it was a prediction by Gordon Moore of Intel, who predicted that technically the transistor density on a chip was going to double every 18 months. And so it starts off in the 1970s with 2K chips, and recently we passed 80 billion transistors on a chip from NVIDIA. So we have been following this computational ability of being able to have more and more computing capability, and it's been phenomenal in terms of the growth here. I worked on the first supercomputer, which was the Iliac 4, and we had 25 megaflops worth of processing capability. Today, you can buy an Xbox, and that has 12 teraflops. And by the way, the first supercomputer, Iliac 4, occupied a huge chunk of real estate out at Moffett Field. The whole idea here is this idea of the fact that by about 2015, 2016, we started to accumulate enough capability to actually have digital twins do the sorts of things with the computing capability that we needed. I'm going to talk a little bit about digital twin types, because there's 3 types of digital twins that you kind of need to understand. And you can see down in the lower left corner my perspective of the product lifecycle, because this needs to encompass the entire product lifecycle. So we have a product-centric world we're moving to from functional-centric, and we create, build, operate, sustain, and dispose of the product. There's not bright lines of demarcation between those 2 points, but that's how I view the product lifecycle management. At the beginning, we basically have a digital twin prototype. And so we have an idea, it's very fuzzy, and it takes form. And by the end of the time that we've developed the product and its means of production, because it's key that we are able to produce the product, otherwise we've just got pretty pictures, we create basically all the products that can be made. And so this is the product and its variants. And the digital twin prototype material will basically be used for the rest of the product lifecycle, because it contains very valuable things like engineering intent. When we start to make, and I'm talking about complex products, not simple products, we have a digital twin instance, which is the actual product that we've made. So instead of having general geometric dimension and tolerance of plus or minus X amount of millimeters, we now have an actual measurement of the things that we've made. And so this digital twin instance gets made at the same time we made the product itself, the physical twin. And what we do is we want to keep that connected throughout the entire life of that product. And these are all the individual products that are made. And as I mentioned, it needs to be a complex product. You're not going to have a digital twin of a paperclip, but you certainly will have, and this is basically a semiconductor processing machine. Where we're going to get some huge value is what I call the digital twin aggregate. So if we aggregate all the instances, we now are going to be collecting data about how they're performing, so that we can do, for example, Bayesian probabilities of how they're performing out in the field when we get certain sensor readings. And so these are all the products that have been made. And so our focus here is we start with the digital twin prototype at the beginning of the life cycle. We start to make these products during the manufacturing phase. And then what we want to do is we want to collect as much of the data and sensoring information off of these products in order to understand how they're actually going to perform in physical use. So I want to take you through the digital twin model throughout its entire life, so you have an understanding of how we have to do this in order to be able to have the right information. We really want to collect the data at its source, because if we have to go recreate it later on in the cycle, it can be magnitudes, or will be magnitudes difference than collecting it at the source. So in the create phase, we basically have what looks like the classic digital twin model, which has the idea that in this particular case, we do all our work over in the virtual space, because what we really like to do is we like to design our product virtually, test the product virtually, manufacture the product virtually, support the product virtually, and only when we get it all right do we want to go out and move around expensive physical atoms. So at the end result of this is we do as much work as we possibly can in virtual space, and then we have a physical product. But it's not enough to have the design and engineering of a product. We have to also have the means of production, because if we don't, all we have is some cool things on computers, but we don't have a physical product. And we with a digital twin, we have to get to a physical product, or we never had a digital twin. We simply have digital models. And so the means of production is important. And so we're using and creating our digital twin prototype, or the prototypical digital twin, at this point in time. The building part is always the most complicated, because in essence, we're changing modes here from virtual to physical. And so what we want to do is we want to take the means of production and feed that to our digital twins of our machines, which are going to be talking to the physical machines, and they're going to be creating the physical products over on the left-hand side. At the same time, we're creating the digital twin instances of those products on the right-hand side, because we've got to capture the as-builds as they're being created, or we're never going to be able to have the as-maintained and as-operated if we don't, in essence, start with the baseline of how the product was made. So we're going to have the digital twin prototyping use, and we're creating our digital twin instance, and we basically are using that data and information. When we basically have the product out and about, which for a lot of products are going to be years, decades, and maybe even longer than that, we want to keep the physical product and its digital twin instance connected and collect that information, and also then create our digital twin aggregate. So we're using the prototype, instance, and aggregate. But this is going to also allow us to do something that we've had a problem with before, and that's closing the loop. And I've seen over and over again where we have version 3 and 4 of the product having the same problems that version 1 did. Why? Because nobody told the engineers how the product actually worked was different than how they thought it was going to work. So we want that feedback loop that goes back into the engineering so we can do a better job on the next version of the product. But I want to spend a minute or two just talking about the physical twin, because again, you've got to have something physical because you actually have to do physical work in our universe. And so the physical twin has certain characteristics that we need to have built into it in order to be able to do the kind of things that we're talking about. So the product needs to be smart. And we've had that since we could put circuit boards in products, but it needs to sense what the environment is. It needs to translate that sensing part into something that we understand, like miles per hour or degrees of temperature. We need to compare that with what we want it to do, and then we want to react. So we're on a spectrum from simply informing us about, hey, there's going to be a problem, to some sort of autonomous act. So for example, cruise control informs us that we're coming up on another car. Adaptive cruise control actually decreases our speed so that we don't hit it. But now we're in the era of smart connected products, or IoT kind of products, which we want to communicate, assess, and respond to something. And we can do that at different time frames. So if we're simply collecting data about, for example, gasoline efficiency, we could collect that once a week. But if it's an airbag going off, obviously that needs to happen immediately. The last thing, and the thing I always emphasize, is it also needs to do protecting. I mean, once we open up a product to sending out data and information, we now have a huge vulnerability. And so we need products to be very, very paranoid about what they do. So some of the things about digital twins are unique in terms of the physical versus virtual universe. The first thing that we want to do is to replicate the product at every time X. We basically collect the information. One of the things I found a saying is we'll never have another Malaysian airline, because we'll know exactly where our airplanes are at all points in time and know what's going on with them. But the replication is we need to basically have the information at every time X. But the digital twin is time unconstrained. We're not. I mean, we can't go into the past, and we can go only into the future with every tick of the clock. We can basically, if we've collected the data in of how it's been operated, we can actually step back in forensics to see where things went different from what we thought. But one of the things I think is a real opportunity is what I call front-running simulation, is that ability at every time X is to be able to predict what's going to happen and to be looking for adverse events that we can prevent from happening. And so at every time X, we basically run a simulation, or will run a simulation of our product to look for adverse events. And now, this may not be deterministic, it may be probabilistic, but at least it would give us an understanding of things that are going to happen that we want to fix before they occur. And so this idea of front-running simulation of every time X, we take our simulation and rerun it, I think is going to be very powerful in terms of preventing issues from occurring. We're also space unconstrained, though. In the physical world, if we have a problem on the other side of the world from an engineer, we've got to put him in or her in an airplane and go fly out to see it. We can actually, in the virtual world, put them together, and so effectively we're kind of space unconstrained. So what we're really going to do to take a model and kind of orient it vertically rather than horizontally is overlay our virtual space onto physical space, so we can do things like augmented reality on physical products and see what's happening inside them as we're repairing them. So this is an opportunity because of IoT and the digital twin of being able to not only have two separate areas, but we can basically merge those areas in AR and VR. I propose that we have an intelligent digital twin in a paper that you'll see there, and I use intelligent, and it should be intelligent-like, but that kind of confuses people, is that basically it's going to act semi-intelligently, but I don't ever believe that these things will be that intelligent that they'll replace humans. But the digital twin is passive, where the intelligent digital twin is always going to be active and always going to be looking for issues. Which makes a digital twin offline, but the intelligent digital twin will be an online, always active kind of agent for us. We give the goals in intelligent digital twin in digital twins, but intelligent digital twins, we can goal seek and minimize resources. And I have this idea that AI, its natural habitat is the virtual world. And finally, the digital twin, we can look at the data and predict it, where the intelligent digital twin is going to be anticipatory. So these are sort of the distinctions, not huge distinctions, but they're basically, we're moving into using AI in order to be able to assist us. And then finally, the digital twin can be security oriented, but the intelligent digital twin needs to be paranoid to protect itself. So I look at AI since on a spectrum from expert systems to the singularity, and those of you who are Terminator fans will recognize the T-1000. But remember, our intelligence is goal-seeking while minimizing scarce resources. But we have dramatically different hardware than the computer AI systems. And so what we really want is what I call acute availability, which I had talked about it as a core component of product lifecycle management from the very beginning, versus human replacements. We do not need human replacements. We have plenty of humans. They just need to be smarter. So this is a potential key to digital twin interoperability, is going to be using AI to help us integrate digital twins. So where are we going? And so where we're going in terms of looking at physical to virtual maturity and in the information evolution is we start off with what I call the traditional era, which is at phase 0. And that is the era that we've been since the beginning of human existence, which is as soon as I had some sort of idea, I had it take physical form, in this case, a blueprint or a physical prototype. The 2000s were kind of amazing in that what I call it the transitional area. We started to be able to do three-dimensional models in computers and also have enough computing capability to do some of the things that we needed to do in terms of modeling and simulation. Where I will contend is where basically in the ad hoc era, we have digital twins, but we basically have to kind of think about how they're going to react, and we have to put them together ourselves. And so we're in the conceptual era of figuring out what digital twins can do for us, and starting to design the sensoring capability on the physical side to be able to give us the data that we're going to need to do the sorts of things that we're talking about. Digital twin platforms are coming, and so replication, the ability of having all the data about our physical things, no matter where they are in the world and no matter where we are in the world, is what I see us doing. And then finally, the digital twin platform, which is front-running simulation, so a crystal ball into the future. This has been a chart that I've used. What we're really going to talk about is the fact that these things are now what we're sort of calling the metaverse, and I'll just spend a minute kind of wrapping that one up. And so one of the things that we have in terms of digital twins is the fact that they need to be interoperative. And so what they require is a thing I call cohesion, which is you put things together in the physical world, and they automatically operate the way they're supposed to because they're based on atoms. So internally, we need interoperability for individual digital twins, and externally for multiple digital twins. So in this particular case, we have an airframe, we have a fuel tank, and we have an engine. And when we fuel the fuel tank, the digital twin, not only does the fuel gauge need to go up on our airplane there, but also the weight of the airplane needs to increase. So we have to enforce this cohesion. And as I said, in the physical world, it's done by material and forces. We don't have to do anything. It actually occurs. If we lengthen the steel beam, the weight of that steel beam increases. In terms of virtual, that requires us to handle the information inputs and the digital processing. We actually have to program that stuff in order to be able to do that. So the potential cohesions for this are, we can ad hoc programming, and that's kind of what's been happening today. And some of them are very successful. It's expensive, but it basically can pull together different digital twins. There's a lot of call for standards, so ontologies, attributes, method call, semantics. The problem is I think we have too many standards, and standards are hard to come by because a lot of cases are political. We can have harmonization, which is we get a group of people to work together in order to be able to agree how they're going to have their digital twins. Middleware companies will come about to in essence, combine different digital twins. We're going to have what I call digital twin metaverse platforms that they'll basically be able to put out their standards, and if you adhere to that, you'll have interoperable digital twins. But I think AI has the ability of taking diverse digital twins, figuring out, in essence, what are the requirements to connect two different digital twins if they have learned it well enough. So I'm just going to finish off and talk about the digital twin metaverse. Our digital twin metaverse has these characteristics from, and this is going to be in a book from Springer coming out next year. That first of all, there'll be multiple DT metaverses. The individual claim was that there was one. It's going to support both replication and prediction. We're going to need all laws of the physical universe implemented and enforced in simulation for all inanimate objects. We're going to have to have digital twin interoperability as a requirement if we allow multiple digital twins. We are going to have immersive capability for participants as avatars, and they can have meta capabilities in terms of being able to, say, teleport from one location to the next, or to change the time. Time can be synchronous or asynchronous with physical time, depending on the use case and the digital twin type. And then finally, we're going to need to embed cybersecurity to begin with. The fortress model, where we can put things in a remote site and protect it with armed guards and fences, doesn't work in the virtual world. So cybersecurity is going to have to be constant and paranoid at all particular points in time. And I just want to show you an example. This is an SLS tank that was tested to destruction for the space tank. Cost hundreds of millions of dollars and months of time to build this and the test equipment. We basically did that in modeling and simulation, And we basically predicted where the test point failure was going to be. And also we were 3% of kind of the load that it took to do that. So there's huge, huge opportunities if we can move into the virtual world in terms of saving physical resources as a trade-off for information. Here are some selected resources. I do have a YouTube channel for presentations, but with that, I want to thank you very much. And not sure what we're doing, but we could open it up for questions or whatever you'd like to do.